All right. First off, I want to say thank you for inviting me to speak to you, to come all the way over to Warsaw from New York City. My name is Alan Johnson. I work for a company called Artsy, and I'm going to talk about a case study of how we use Scala plus associated technologies to build our real-time auction engine. So one of the things that I often get asked is, where do you even get started in Scala? And at my company, which doesn't have a major background in Scala or functional programming or typed languages, there were certain challenges in trying to bring in this technology to solve our problems. So kind of inspired by this artwork on the right side, I don't know how to pronounce the photographer's name. I think Aiden Buyuktas. I'm going to start from the very kind of overview level of what our business does, what my segment of the business does, and then kind of drill down into like the core technology from the problems that we were trying to solve, because that's what ultimately drove our decision to adopt the technologies that we did. And at the end of the day, we're probably going to, there's only a little bit of code in my presentation. I'll be preaching a bit to the choir, I imagine, since we're all here to talk about Scala. But for anyone who's ever had to make the case to perhaps like a skeptical business folks of why Scala could be useful to solve a technical problem, perhaps this presentation will be useful. So who are we at Artsy? We're the leading destination for exploring and collecting art from the world's largest network of galleries, museums, art fairs, and auction houses. We're located in New York, but we have people worldwide. My part of the company is the auctions engineering team, of which I'm the team lead. There's 6 of us now. We are responsible for a wide range of software, front-end and back-end systems for allowing people to bid in online-only auctions that are hosted on Artsy, tools for managing those auctions, the ability, we provide a tool for allowing people who are interested in selling artwork to find auction houses who are willing to consign that artwork. And what we'll talk about today specifically is live auction integration, which is basically allowing people to bid in real time in auctions that are happening physically at the auction house through our online system. So of this 6-person team, at the time we were working on this project, we didn't have our newest members, Eric and Chris, so there were 4 of us, and we were spread amongst all the front end and back end and mobile native parts of the stack for this new product. And of the 4 of us, this is the one who knew Scala at the beginning of this project. So it's, thank you. So while the language maybe rightfully has a reputation for being difficult to learn, it's not impossible for a team to learn it in the course of building software on a tight deadline. We built this in 6 months, so it was pretty stringent. So to talk a little bit about the problem we were trying to solve, what you see in the upper right is an auction that we allowed people to bid on online. So at a typical auction, you have an auctioneer who is the ultimate source of truth for what's going on in the sale. You also have people who are bidding, some of whom are in the room. Other people, you have auction house staff that are on the phones talking to, and they bid on their behalf. And then you have online platforms like ours that allow people to bid remotely through like a web or mobile native interface. So our business goal is to get these bids from Artsy bidders into the room to the auctioneer. But the tricky part about this is we don't actually control the sale. It's not like our back-end systems are the source of truth for what's happened. We have to be flexible and work around what's actually going on in the physical world. So for what we're trying to do from a technical standpoint is make sure that when someone bids, that our person in the room gets that information as fast as possible so they can compete with the people who are there just listening directly to the auctioneer. And in the lower right, you can see what happens, or a sketch of like how this works kind of schematically in the best case scenario. So you have a whole bunch of people, the bidder and the people who are all watching, and they're participating with either through their browsers or their mobile native clients. So the person who's interested in bidding places a bid through their interface. Via WebSocket connection, that bid gets submitted to our bidding engine. Then the bidding engine determines whether this should be accepted as something that happened in the course of the auction or not. And let's say that it is. That doesn't mean that the bidder is going to be informed that they're winning yet, because we're not the source of truth. But we can reject it in other situations, like if we know that another bid has come in, then perhaps they'll get rejected. But for argument's sake, let's say that the bid looks good, we accept it, so then it's reflected on the screen of one of our operators who's sitting in the room that they have a new Artsy bid and they should raise their hand and bid in the room. The auctioneer, who is ultimately the source of truth of this sale, acknowledges, says we have $10,000 to the Artsy bidder, and then a separate person who also works for Artsy, their job is to record everything that's going on in the room so that everyone online has an accurate representation of what the current price is and the state of that auction. So through their web client, they press a button to acknowledge that our bidder has that increment of the bidding. That goes back into the bidding engine, that confirms that bid, and then that gets broadcasted over the WebSocket connections of all of the participants and the original bidder. So that's the happy path. It's this system that involves like multiple humans in the loop, and so it's a little tricky to get right. And we had to account for this process as well as all of the possible things that can go awry, of which we've seen well, I guess we haven't seen everything, because now every sale we do, we see some new thing that we didn't imagine. So the system had to be flexible in order to be able to deal with things that even we couldn't account for. All right, so some of the requirements are a little unusual. So our system is very low throughput in terms of like what the demands placed on it, compared to a lot of systems they're dealing with, like real-time automated bidding auctions, like for finance or ad tech. Our throughput is super low. So most of the time, we're taking advance bids for sales that are going to happen in the future, and 10 events per hour would be like high load for us. So it's very, very low throughput. And then in the most bursty situation where there is a live sale going on, like let's just say for argument's sake, 10 events per second is about the fastest input of events that we're ever going to see. And that would be absurd. I don't even know how that would happen, that our operator and our bidders would press buttons, 10 of them all within 1 second. But for argument's sake, let's say that that's like the cap. So although we have like a very low throughput, each of these events has a great deal of value. So we regularly see bids in like the 5 or 6 figure amount of dollars. So it's very important that this whole process be reliable. It's important that everyone sees the same price. So I guess you could say we are looking for a system where like throughput isn't really our goal. So we don't really want to be in like the AP zone of like the consistency, availability, partition resistance. We want to be in like firmly in CP, where everyone sees the exact consistent state of the world. And if something goes wrong, we would rather just fail than to tell a whole bunch of people a bunch of different prices, or that 3 different people won the item. That would be a bigger disaster than just not being available. So kind of along with that, we don't do optimistic updates. We want to tell you after the auctioneer has confirmed that the Artsy bidder is the winning bidder. That's when we'll tell you that you're the winning bidder, to avoid any sort of confusion. In the middle of this is a whole bunch of kind of complex domain logic about how auctions work and all the different rules. And then we also wanted the system to be extensible. to support things like undos if something, the auctioneer, pretty regularly, the state of the auction has to be rolled back for whatever reason. Either maybe our operator pressed the wrong button, or the auctioneer gave the bid to the wrong person and they corrected. So we have to be able to work around all these things. And then it's also useful to be able to query the historical state of a sale. So all these things kind of led us to a decision to go with event sourcing as the way that we stored our record of what's going on in the sale, to allow for that historical query, and also to model all of our domain logic as events that can be validated in of their own right, and really tightly control the allowed state transitions within the system. So to talk a little bit about how this system is architected, we're not going to go through all the pieces of this at all. We're going to focus specifically on the auction logic service and our store and cache service. But generally speaking, this server is organized as a stack of services that are all linked together with functional dependencies, which I probably won't have much time to get into. This timer isn't running. Is that? If it's stuck at 10.
Yep, it is 7. You have 90 minutes.
Oh, okay, good. Perfect. All right, so that's more than I thought. That'll work. So everything's hooked together with what I call functional dependency injection, and we'll talk about that a little bit because I think dependency injection is a very popular topic in the Scala ecosystem. So things come in via either our HTTP or WebSocket APIs, which are implemented in Akka HTTP. And if you've worked in that, you know that their WebSocket interface is built around Akka streams. So our actual event persistence is using Akka Persistence with a library we developed called Atomic Store to provide for the consistency that we're looking for. We use Spray JSON Shapeless to cut a lot of the boilerplate out of serializing for our APIs. We use Akka Cluster and distributed pub sub in order to give ourselves the availability that we want and to serve the load. We use generative testing with Scala tests and Scala check. Use some caching with a library called Mango. Our authorization, we use a library that's built on JWT, JSON Web Tokens, and Slick, Flyway, and Postgres for relational storage. And then we've been experimenting with Akka distributed data for like kind of runtime configuration. So it was cool to see the talk yesterday on that. All right, so to get into kind of like the nitty gritty of how we actually process events. So while a live sale is going on, events will come in over a WebSocket interface, and they go through this process that one of our services called Lot Event Logic provides, called post event. So in will come an event that communicates via Akka with Atomic Store, which is where our events are. It's sort of responsible for the persistence of these events and like the canonical record of what's happened in the auction. So this process is initiated with a message called store if valid. And then what will happen is that at that point in time, Atomic Store goes into this busy state. And I should pause by saying one of the reasons we use this Atomic Store abstraction built on top of Akka Persistence is that we wanted to factor out the actual storage and the atomicity from anything that's in our domain model. So Atomic Store has no concept of auctions whatsoever. It just knows how to store events, just blobs of data that are scoped to some aggregate while holding off any other changes until validations happen. So Atomic Store doesn't know how to validate whether an event should or shouldn't be persisted. It actually delegates that right back to whoever called it. And in the meantime, it enters this busy state, during which time, if it's going to take I mean, it doesn't take more than a couple milliseconds to validate an event, but let's say another bid came in the meantime. That bid's going to be stashed until we've re-entered the ready state. So Atomic Store immediately responds back with this validation request, which comes packed within it the entire sequence of events that's happened up until this point. So then event logic post-event is again responsible for validating whether this new event should be allowed. So it instantiates what we call an auction calculator, and this is where all of our domain logic for calculating the current state of the sale, so that might be what the current price is, what the asking price is for the next bid that has to come in, who the winner is, how many bids we've had, how much revenue's been raised. All these calculations are done statelessly within this auction calculator. So auction calculator is instantiated with a record of all the prior events that have happened, and it can answer the question of whether this new event that's come in over the WebSocket should or shouldn't be persisted. So let's say that everything looks good. It sends a validation response that indicates that, yep, we want to persist this new event. Atomic Store persists it, and then sends back a result which just has now the new canonical record of events that have happened within this lot, which post-event's last responsibility is to make a new auction calculator, calculate all the derived state from the new record of events, all the past events plus this new one, and then over Akka distributed pub sub, announce that to all of the observers, all the participants in the auction, that a new event has happened and we have a new price, and that's how everyone sees this kind of consistent view of what happened. And then if you see in the far right, Atomic Store is now back in the ready state so that it can accept new events. So it's just a very simple finite state machine with two states. All right, and so this bidding engine, as I mentioned, works on like this append-only record of events that have happened. So if you look on the left of this, well, I guess the left side of the right side, you can kind of see what we're going for here. So on the left pane, we have like just a record of raw JSON of these events, and on the right side, we have sort of the state that we derive from them. And that's the job of this auction calculator. So the calculators are stateless because that makes it far more easy for us to be able to test whether the logic in the calculator is correct. And then every possible state transition is modeled as some new event, like that a bid has been placed, or that the reserve amount for the lot has changed, or the bidding is ended, or what have you. All these things are new events that get persisted. All right, and so how we provide for high availability and performance, we use Akka cluster, and we use manual load balancing between roles, which is basically to say that we want to make sure that we provide the highest possible performance to our operator who's in the room, who's kind of doing command and control of this whole system, as well as the people who are actually bidding. So when their clients connect, they connect with a URL that points them to the half of our cluster that's dedicated to serving them. Because we also allow people who aren't registered to bid to watch the sale. And we wanted to make sure that no matter how many people are simply observing the sale, that they are never going to impact the performance of the people who are actually placing bids. At the moment, every node is identical. It contains the full service stack. And then we use cluster singleton to ensure that at most one copy of Atomic Store is running in the cluster. At the moment, for all the lots that are going on in all sales, the cluster singleton is going to materialize them on the oldest node. So, if that ever turns out to be a performance issue, which it isn't today, we could switch to using cluster sharding instead to spread the load. But as you can kind of see in the figure to the right, we show how only one Atomic Store exists across this cluster. And then distributed pub sub is how everything stays in sync and how the changes are broadcast to all the subscribers to the WebSocket. Cool. Oh yeah, and then internally, all of the messages are encoded as protocol buffers for performance. So since I have a little bit of time left, I'm going to talk a little bit about how we structure our service stack. So going to conferences, as I'm sure most of you all have, I feel like the argument of how to do dependency injection in various ways is all the rage, whether it's using free or reader monad or constructor arguments or juice or whatever. One of the things that was kind of a constraint in doing this project with a team of people who are really new to Scala is I wanted to be extremely careful to only use technologies in the Scala ecosystem that I could very easily explain and onboard people. And so we settled on a method of wiring up our dependencies that it isn't automatic, but it's ultimately pretty simple to understand, which is kind of similar to the constructor arguments method with one little twist. So this lot event logic class we'll call like a service bundle, and its methods are like the individual services that it provides. And they share most of the same dependencies in terms of the lower level services that they need to do their work. So it provides 3 services: event for lot ID, post event with params, and a regular post event. That they're all just public methods. So in this kind of structure of dependency wiring, public methods equals services within some case class that is a bundle of services. And then there's some private methods that just like for any internal kind of like helper type stuff that needs to be included. Dependencies are modeled as just functions. So all of them are basically functions that take some data and return a future of some other data, perhaps wrapped in some result type. And then for anything that's kind of like more like a framework dependency and not really like a service and like our domain model, we use just implicits to wire those things together. And that way all of the main APIs don't necessarily have to mention their implicit parameters, and everything else can be more or less focused on what's meaningful from a business level. And then the way that it's all wired together, at the moment it's all done manually, but we have a fairly small number of services, so it's not too painful. But essentially, we just instantiate every service, passing in as its dependencies the methods of other services, relying on Scala's ADA conversion to convert those methods into anonymous functions that match back to the constructor arguments that are on the case class that represents the bundle of those services. So that's been really simple, and it also makes it really easy to mock everything for testing. In order to mock out lot event logic, if I just want to test like the basic functionality, all I need is something that takes a string and returns a future of something, I just have to match these 3 constructor arguments, the anonymous functions they require, and it makes testing quite simple. I don't have to mock out like a whole interface of a service or anything like that. And it's sort of arbitrary, the granularity at which we want to divide up these bundles, but we just choose what feels comfortable to us. And if anything becomes unwieldy, we can always break it up and make it more granular. And we kind of just allow the ergonomics of working with it to drive it. And then I suppose if we ever get to a point where we have so many services that the boilerplate of wiring them all up is unbearable, I'm sure we can apply some of the tools from the Shapeless workshop in order to automatically wire this up, or use juice, or whatever other kind of like meta framework for automating the wiring we might want. All right, and so with that, that's, oh yeah, I should talk about the outcomes. So this whole system, as well as the clients that depend on it, the desktop mobile web interface and mobile native interface, we managed to do the vast majority of that work in about 6 months. So from December 2015 through June 2016. Got the other developers onboarded into Scala, although it's still like an ongoing process to get them like fully comfortable with working on every aspect of the stack. But everybody has made major contributions, so that was a big success story. And I think that on the whole, it was a good case study for how much mileage you can get. We wouldn't have been able to launch this thing in 6 months if so much of the functionality we depend on wasn't provided out of the box by frameworks like Akka. We found that so much of what we wanted to do more or less exactly matched up with different aspects that Akka provides just out of the box. And it was really just a matter of reading the documentation and configuring them for our needs and kind of wiring them up with our domain model. So most of our actual code tends to be focused on things that we actually care about. The performance has been great. We run this on a cluster of, I believe it's just like 3 machines, the regular size Amazon instances. And so far it's coped with the variation of things that we see, all the things that we didn't plan for. And we have a pretty strong platform for a whole bunch of future extensions that we plan. So with that, I'm going to wrap it up, and I think we have about 3.5 minutes for any questions. Thank you.
Okay.